So for coin flips, okay, the sample space is head and tail, right? Okay, so that's relatively easy, okay, because it's discrete, okay, because it's discrete. But how about, okay, the situation, okay, like, okay, American woman, okay, the average height of American woman, okay, actually, most of the, I mean, I used to be in like Midwest, okay, Indiana and Ohio State, and then I spent 6 years like in Alabama, okay, which is considered the southeast of the U.S., okay, you know, as a professor there. So actually from my observation, okay, like the American woman, okay, on average is not so tall, okay. It's well, I probably a little bit taller than Taiwanese woman, okay, but you know, but not a lot, not a lot. But of course that's based on my own observation, okay, because I do understand like if you go to like a north part of the U.S., okay, the people there are actually taller, okay. I don't know why, okay, but the people, for example, living in like Minnesota or like Wisconsin, okay, people living there are, I mean, they are, you know, taller on average, okay. So so because I don't have like a experience living in that area, so I don't know, but you know, so we might believe the average American woman is 5'4", okay. 5'4" is like 大概多少？大概164、165公分吧 ，okay, like about 164 centimeters, okay, something like that, okay. I think like a lot of the Taiwanese women are taller than that, right? So, but anyway, like that's the no, we may believe that, okay. But what is the sample space here? Because we are talking about the height, right? So you know, it could be 5'4", it could be 5'3", it could be 5'3.5", it could be, you know, because it's a continuous space, right? It's a continuous sample space. So there will be too many possible outcomes in this sample space. So, you know, in the previous example, like a coin flip, because we have only 2 outcomes, so we can describe the probability of those 2 outcomes by a very easy, like for example, like a histogram, okay, because there are only 2 possible value, 2 possible like outcome. So for each outcome, you have 1 probability. That's it. But for this one, okay, because we have infinite number of sample space, so we may instead describe the degree of belief by a bell-shaped curve. That because we believe like it's 5'4", right? So the highest, this bell-shaped curve is highest at 5'4", and it drops off symmetrically above and below that 5'4". Okay, so this actually is just like normal distribution. Okay, you can change the width and the center of the curve until it seems to best capture your subjective belief, because different person has different belief, as I say that. Okay, so I keep saying that. So normal distribution, okay, a probability whether it's outside the head or inside the head, okay, is just a way of assigning numbers to a set of mutually exclusive possibilities. But so now we need to talk about probability, right? We need to talk about probability. So you know, for a probability distribution, okay, for something that has to become a probability distribution, something that has to become a probability, okay, to describe a certain event, okay, then the probability needs to satisfy the following three properties. Okay, this is very important. Okay, the first one, a probability value must be non-negative. You can never have lower than 0 probability value. So you could have 0 probability, you could have positive probability, but no negative probability. The second, the sum of probabilities across all events, okay, in the entire sample space must be 1, okay, because you know once you consider all the possibilities, okay, you add them up, the probability must be 1, okay. The third one, for any two mutually exclusive events, okay, be careful, they have to be mutually exclusive events. When A happens, B cannot happen. When B happens, A cannot be there, okay. So if there are two mutually exclusive events, the probability that one or the other occurs, okay, is the sum of their individual probabilities. So this third one is also very important, okay. So these three properties together, okay, if something satisfies all these three probabilities, we can say it's a probability distribution, okay, of an event, okay, something like that, okay. So it could be discrete, it could be continuous, okay. So, for discrete like situation, it's very easy to describe, but for continuous events, so it's more difficult. But for even if it's a continuous outcome space, we can discretize the space into finite set of mutually exclusive and exhaustive bins. Okay, for example, the x-axis denote the height. Okay, and the y-axis denote the number of person, and we try to we collect the data. We try to collect like the sample here is 10,000. Okay, we have 10,000 American women. Okay, their heights. Okay, we get the data set from these 10,000 American women, their height, and we put their height on this here. Each point represent one woman in this data set, okay, and you can see that, okay, it's very dense in the center, and much you have much lower number of women on the two sides of this distribution. Okay, and here, okay, we try to discretize. Okay, in the sense that each bin, okay, we try to consider like 2 inch as wide as one bin. Okay, so for example, 55. Okay, this bin is 53 to 55. This bin is 51 to 53, and this is 55 to 57, and so on. Okay, so we divide this continuous sample space into some number of bins. This is we discretize the continuous event. continuous sample space into, discrete like outcomes. So each bin, okay, will consist of like the height in between these two numbers. Okay. So once you put discretize this space into the finite set of mutually exclusive bins, then you can sort of like use a histogram to describe all these women, okay, their height, okay, in this histogram, okay, and then you can divide, okay. Originally, okay, you can put down like, okay, I mean the y-axis originally could be number of women, okay, with that fall into a certain bins. But once you divide the number of women that that fall into certain bins with the number of samples, what you have is this probability density here. Okay? So in particular, number of measurements that fall within the interval 63 inches to 65 inches is 1,473. Okay, which means that the estimated probability of falling in that interval is 1473 divided by 10,000. It's 0.1473. So it's well, he's talking about 63 to 65, right? So this one. So this is actually referring to, okay, this actually referring to probability mass. Okay, probability mass. Okay, this one referring to probability mass. Okay, number of occurrences divided by the total number of the instances. Okay, in a certain bin, but because it's a continuous outcome space. Okay, so we can another way to divide this is that, okay, for example, we can divide like each bin as 1 inch, okay, in width. Okay, if you do that, then obviously, okay, you can see it's going to be you have more number of bins, and the probability mass will look very similar, but it's going to be, what should I say? Like it's going to be the granularity is going to be much thinner. Okay, it's going to be the resolution is going to be much better. Okay, but it's obviously like both this one and this one, they both look like a bell shape, right? And also, if you say, okay, what I want to consider, originally I will talk about probability mass, but you can also talk about probability here. Where is it? Okay. No. I think this one. Okay. The probability mass, for probability mass, we know like it satisfies all those three requirements. Okay, like the first one, I mean, for each bin, the probability mass, like the result is greater or equal to 0, right? And also, I mean, if you add up all the event points, across all the bins, okay, it's going to be equivalent to the denominator, the total number of events. So the probability add up will, across all the bins will be 1. And the third one, okay, for two different bins, the chance for a height that fall into either one of them is the sum of these two bins, because each bin is mutually, these bins are mutually exclusive. Okay, so probability mass, okay, is a probability density. It's a probability distribution. Okay, but another way to describe that is, probability. You can divide the probability mass with the bin width. Okay, that's called the probability density. Okay, so for example, okay, originally like this one, when you divide the probability mass with the bin, which is in this case is bin width is 2, so it's going to be 0.074. But once you divide this one with bin width, okay, because bin width is 1, so it's going to be 0.066. Okay, and you can easily do a very simple and a quick observation that probability density is also a probability distribution. Okay, it also satisfies those three properties. But one thing very, very interesting is that, okay, let's consider another case. Okay, in this case, we also have like 10,000 samples. Okay, 10,000 randomly selected doors that are manufactured to be 7 feet tall. Okay, so we go to stores to purchase door. Okay, that are supposed to be 7 feet tall. Okay, and then we measure the height of the door. Okay, you can imagine because originally when we measure the height of American women, okay, the average height obviously is not. It's going to be the height of the American women is going to be distributed much widely, right? But now, if you consider the doors that are manufactured to be 7 feet tall, and you measure it, obviously, because it is manufactured to be 7 feet tall, so the height must be close to 7 feet, right? Okay, actually, it's if you look at it, what is 7 feet, by the way? 7 feet in inch. It's 12 times 7, right? 84, right? Right? You know the conversion between inch and the feet, right? Each feet is 12 inch. So when we say 7 feet, each foot is 7 inch. So when you say 7 feet tall, that's 84 inches. So if you can look at that, 84 inches obviously has the most number of, of course it is still continuous space. We're still doing this discretization, okay? But now, okay, this bin width is much narrower because obviously, this door height are very, very close to 7 feet anyway. Okay, so beam width is actually 0.025. Okay, 0.025 inch. The difference is, I mean, each width is, each beam width is very, very narrow. But you still see like most of the population, okay, will be close to 84 inches. That's obviously, okay. But you can see like, I mean, also some manufacturers are doing a very poor job, right? So because you can even see some occasion like it is like 83.6 inch. You can see one occasion in here. That's actually 0.4 inches difference. 0.4 inches is more than 1 centimeter. Okay, that's considered a lot. Okay, when it comes to door manufacturing. Okay, same thing goes for like the other end. Okay, here it's close to 84.4. So again, it's a more than 1 centimeter difference. Then the specification, because specification is 7 feet tall. Okay, so we have 10,000 doors and their heights are here. Okay, and when you calculate, okay, one interesting thing is, I mean, obviously you can calculate probability mass, and for each probability mass, the probability mass for each beam is again, okay, greater or equal to 0. But when it comes to probability density, okay, remember I say, I mean, when it comes to probability density, because you need to divide the probability mass with the beam width. So for example, if you divide the probability mass with beam width for this particular example, okay, you will get 2.829. So you say, wait a moment, this is a probability, right? How come probability can be greater than 1? This one is greater than 1, not to mention the other. This part, they are all greater than 1, by the way. Okay? But that's okay. Why? Because if we check out these 3 requirements for probability density, does it ever mention that probability, any probability distribution, like a reading of a probability, I mean, for a certain situation cannot exceed 1? It doesn't say that, right? These 3 properties does not say anything about a probability cannot be greater than 1. Okay, even though it may, be against your intuition. Okay, I just want you guys to understand. Okay, for probability mass, because it's defined by the number of occurrences divided by number of total samples, okay, for any beam. So the probability mass can never exceed 1. But for probability density, it's different thing, okay, because you have to further divide it, the probability mass, by the width of the beam. So it could be greater than 1, okay? So, well, the probability mass of the ith interval, okay, is denoted as this, okay? And we know the sum of this is 1, okay? And we know, like, for example, okay, if we do, this is probability density, right? This is probability density. and the sum of the delta x times this probability density, okay, will also be 1, okay, which can be described like this. I mean, by the way, the book, okay, the Doing Bayesian Data Analysis book, the author obviously is not in mathematics department, because this dx, okay, in math department, they normally put it at the end, right? It should be, integral px dx. Okay, but that author likes to put the dx, in the front. I just want you guys to understand this is, integral px dx. Okay, not integral dx px. I mean, well, but you get the idea. Okay. So because this one looks more like that. Okay, so well, just to want you guys to understand that. So the integral of the probability density is still going to be 1, regardless. So probability density obviously is a probability distribution. Okay. So when this delta x is is getting smaller and smaller, okay, we normally do not consider probability mass. We normally consider probability density, okay, or you can consider that as a continuous case, okay. So for the most famous probability density function that has been used, okay, is normal distribution, or another way to call it is Gaussian distribution. Okay, it looks like this. It's a bell shape. Okay, the mathematical formula, it looks like this. Okay, and the important parameter for this distribution, are the mean, okay, which is denoted as mu, and the standard deviation, which is denoted as sigma. Okay, and the mu determine where the center is located. Okay, and the sigma determine how wide this bell shape looks like. Okay, so we define a random variable x by writing stats.norm, okay, mu sigma, okay. This because we are talking about normal distribution. Okay. This is SciPy, by the way. Okay, so we can get an instance x from this using RVS, okay, random variable method. Okay, so in the example below, okay, we ask for 3 values: mu equal to 0, sigma equal to 1. This is the standard normal distribution that we usually talk about, like with mean 0 and the standard deviation 1. Okay, and then we create the random variable x, this capital X, okay, by using the mu and the sigma, and then we try to get 3 samples from this distribution, okay, and put them in lowercase x. So, so common notation in statistics, okay, to indicate that a variable is distributed as normal distribution, okay, with parameter mu and the sigma is like this. X, okay, this small delta, you can say this. You can translate this small delta as like is distributed as. Okay, so when this n obviously refer to normal distribution with parameter mu and sigma. So you can translate this formula as x is distributed as normal distribution with mu average and standard deviation sigma. Okay. So then, okay, we weighted each possible outcomes by the probability that it happens. So this procedure defines the mean of a probability distribution. Okay, we call it, another way to call the mean is expected value, okay, which can be written as E of EX, okay. So it's basically it's defined as like a PX times X and the summation. Of course, this is discrete form. Like if it's continuous, then it's a like a PXX dx. Okay. Again, let me remind you, this dx should be put like at the back. Okay. So that's like a expected value or mean. Okay. I mean in statistics. Okay. So here, okay, we can consider the probability density function px equal to 6x 1 minus x, and which is defined over the interval x in the range of 0, 1. And you can compute the ex, okay, like this. Okay, so I will not go into the detail. This is a very simple integration anyway, right? So the result is 0.5. But one thing I would like to ask you is that, okay, before you calculate this average, the first thing you should calculate is that, actually, is whether or not this density function really is a probability distribution. Okay? If I ask you, is this a probability distribution? What should you check? Remember those three properties? The first one, in between 0 and 1, is this density function always positive or 0? Yes, right? Yes, right? Okay. The second one, the third one, like mutually exclusive, like the probability add up to be the event for those two. Like this is obviously true, but the second one needs to be verified, right? Okay. In other words, the first thing you should verify is perhaps this is oh, sorry, there's a 6. The first one you should verify is this one. Okay, this is the second property, remember? Okay, you have to ensure this is a probability distribution. Okay, and then you can try to calculate the average of this distribution. Okay, like this. Okay, but I think this is also very easy. I will not go into detail, but if you have trouble doing this integral, let me know. It's still early. We can drop this class, okay? Because this is really freshman calculus or high school calculus. Well, you should have learned that, okay? But if you already forget everything, that's fine. That's fine. I mean, it's just like you can take some other classes. This class is probably not for you. Okay. So just want you to understand, how do you verify a density function is a density function, is a probability density function. Okay. And then, how to calculate the expected value from a probability distribution. Okay. Okay. So, by the way, I mean, some students ask me like, okay, in the homework and exam, am I going to assign like a computational type of question? Yeah, that's possible. For example, something like this. But I suppose the computation doesn't, as long as you have the concept, it should be relatively easy, right? Okay, it should be relatively easy. So, the variance, okay, of a probability distribution, okay, really can be defined as like the square difference between x and the mean. So it's I mean, if you write it in like formula, it's going to be something like that. So px times x minus ex squared, and you integrate that over all the x range. Okay, so that's a bar x. Actually, I mean, for the probability distribution, this one will lead to standard deviation. Okay, and obviously this one can have a discrete version as well. I will not go into detail. This is very simple. Okay, how do you compute this? I mean, how do you, convert this one into a discrete version? I mean, you can do that yourself. So in normal distribution, about 34% of the distribution lies between mu and the mu plus sigma. Okay, so in other words, if it's in between mu minus sigma to mu plus sigma, okay, within these two sigma range, okay, you have 68% of the data in this range, or you can say it's close to 70%. Okay, because I mean, if you talk to like Americans, I mean they normally like treat the number very inaccurately. So I mean 68%, they will say oh, it's about 70%. But you get the idea, okay? Yeah, I mean the majority of the instances fall in between mu minus sigma to mu plus sigma. Okay, so this gives you a rule of thumb. Like if you want to consider the majority range, like what range you should consider. Okay, but this is only good for normal distribution, and it may not work well for the other distribution. Okay, so do not overgeneralize this fact to the other distributions. Okay, but I would say that, okay, a lot of distributions, if you if you try to do what we say about, I mean, like a convolution, okay, you try to add a lot of like distribution together, eventually it's going to approximate a normal distribution. Okay, so if it's like a very complicated situation, a lot of time you can use a normal distribution to approximate that like very well. Okay, so normal distribution is actually like very convenient, and that's also why it is the distribution that has been used the most. Okay. So the probability can be interpreted, I mean, either as how much a value could be sampled from a generative process, okay, or as how much credibility the value has relative to other values. So you can see the first explanation is more frequentist approach. The second explanation is more Bayesian approach. Okay, but they are somewhat like similar anyway. Okay, because we already talked about this credibility. Okay, I mean, or belief. Okay, you can actually calibrate that anyway, right? So, okay, when P of theta represent the credibility value of theta instead of the probability of sampling theta, then the mean of P of theta can be thought of as a value of theta that represents a typical credible value. So the mean will become the most credible value. Okay, the standard deviation of theta, which measures how wide the distribution is, okay, can be thought of as a measure of uncertainty across credible candidate value. So how uncertain you have for your belief, because remember the belief, okay, the most credible or most the best way to describe your belief is the mean, right? Okay, but how uncertain, I mean, is your belief? I mean, can be measured by the standard deviation. Okay, if the standard deviation is large, then it means you do not believe that so well. Okay, but if you believe that very, very much, then the standard deviation value should be small. Okay, so just to give you some idea. Okay, so okay, it doesn't matter what the value of mu is, because mu just means the center location. Okay, but the important thing is the sigma. Okay, you can see the difference between. I mean, of course, I mean, for this 9 figure, okay, the column have the same mu with same sigma with different mu. The row, okay, the figures in a row has the same mu, but with a different sigma. Okay, you can see mu control where the center is located, and the sigma control how wide the distribution is. I mean, when the distribution becomes wider, the height, the highest point is also reduced. Okay, highest points will also become lower, because well, the integral of this will be 1 anyway, right? Okay, so when it's wider, obviously if you want the integral to be the same value, then the height of mean will be reduced. And in this discussion, I have never mentioned that the value of any point here, okay, is greater than 1 or not. It doesn't matter, right? It doesn't matter, as I have shown you, by that door example, okay, because we are talking about probability density function here. So some of these values, okay, could be greater than 1, but that's fine. That's fine. Okay, it's okay for probability density function to be greater than 1 at some point. That's not a problem. Okay, so that's well, it's already 55. Let's take 10 minutes break. When we come back, we will discuss this joint probability. Okay.